Coming up next on the IP Talk stage, Mike Thompson from Synopsys, presenting audio IP subsystems made easy with an integrated SoC-ready solution.
All right, today I'm talking to you about our audio subsystem, and I actually talk loud. Is this too loud? Fine, okay. That we introduced about a month ago. This is really the first real subsystem, IP subsystem available in the market. I've been in this business for about 30 years, and this has been sort of the holy grail, if you will, and we finally have done it. And I'll show you why it's the only real one. Even though a lot of people talk about having subsystems and making subsystems available to you, they're really not. So obviously, we've been introducing IP into the market for some time. This is part of the disaggregation that's continued in the semiconductor space that started back actually in the 70s. You probably don't remember, but most semiconductor companies back in the 70s had their own fabs. Very few do today, right? Now, more and more semiconductor companies are using IP. You were just hearing a talk before about ARM, which is also an IP vendor. But what's happening is semiconductors are getting so large that it's hard to integrate all the IP in the time available to do it. And companies are moving now to subsystem implementation. So we actually brought the subsystem out in the audio space. What's happening in audio? Audio is not a center of competence for most companies today. It's very important on a chip that requires audio. You can imagine a cell phone chip that didn't have audio wouldn't be much good, or a DTV chip. Actually, there was a study done where they took two identical TVs, and they put very good quality audio on one, and they put just, kind of regular TV kind of audio on the other. People consistently rated the picture quality of the TV with the good audio better. So good audio makes great products. Audio is very important, but again, it's not our center of competence for most companies today. And the reason for that is because audio has gotten very complex. Anything that's connected to the internet has to be able to decode a number of formats. It's not just MP3. We actually support about 90 codecs today. So it's quite a range. In addition, you've got all the multi-channel content. Stereo going to 5-in-1, 7-in-1. We actually have requests now for 9-in-1. I'm waiting, for 11-in-1, 35-in-1. I'm not sure what they do at some point. Not only that, there's higher sampling rates because people want better quality in the audio. Better quality in means better quality out, especially through the compression. And then finally, there's the whole sound processing that's going on. It's become very critical. If you look at a cell phone, for instance, in my cell phone, the speakers are actually in the back, and it's two speakers. Can you imagine a little space like that? And those are not exactly high-quality speakers. They have to be obviously very thin. They're very small, almost no magnet. But the sound quality of that phone can be very good because of the post-processing that's done. So we take the audio stream as it comes out, and we process it to match it to the speakers, and you can make the sound quality very good. At the same time, you can take that sound and you can create virtual surround fields and other things like that. So there's a lot of post-processing that's required, again, to make products sound very good no matter what environment they're offered in. So what we have done is we brought out an audio subsystem. It includes the complete hardware implementation, the complete software stack that runs on it. And we've also, because we offer FPGA prototyping environments as well as virtual prototyping environments, we brought up the capability with those as well. Now, in this area, it would be likely that someone perhaps is running a big little environment, right? But they want to put an audio subsystem on that because these audio chips, the audio processor uses about 1/10 the power of an A7. So if you're playing an MP3 on your phone, you burn up the battery with the A7, but with the audio processor, you can run it all day. But you can actually virtually model that big little. We just announced that we have that capability. And then you can virtually model the subsystem. You can put it into FPGAs, however you want to run it, even with an actual chip. So the subsystem is completely pre-integrated, both hardware and software. Of course, it is available with the virtual environment, but it's also configurable. And the reason we did that is because, again, we don't know the environment that you're going to put it into, so we make it as flexible as possible so that you can tailor it specifically into your environment. And again, the configuration tools allow you to adjust a lot of the different parameters in the subsystem, and it configures not just the hardware but also the software appropriately. So this is the hardware portion, and the subsystem is what's in the square here. It includes an ARC audio processor, and that can be either a single or a dual core processor depending on what you wanted, with a lot of clock circuitry, some memory. This is just an interface, or I shouldn't say just an interface. This is an interface to A to D, D to A if you're doing an analog input-output, or you can have the digital I2S, SPDIF. These are configurable. You can put as many as you want on your subsystem. There's no limit. On the system side, we have an AXI HB bus interface that allows you to get to a host processor. This subsystem is host agnostic. We don't care if you're running with ARM, MIPS, Intel, even an ARC processor. Yeah, there you go. You connect to system memory as well as interfaces, so HDMI, MIPI, whatever you're running on the interface side. It's complete hardware implementation. The ARC processor, if you will. These are the ARC audio processors. Again, it's single core, dual core. You can see a little bit of the processing capacity in the single core as well as the dual core. The dual core obviously has twice as much processing capacity, depending on what you want to do. We see a lot of different models that customers have, whether it's running HD audio on both cores and splitting the task across there, perhaps running the codecs on one core and doing the post-processing on the other. We have a customer that's doing all the audio processing on one core and making the other core available to their customer to do what they want. The dual core implementation, if you go there, also runs at a lower power factor. It gives you a great deal more performance, twice as much performance, but the power consumption doesn't increase by 2x. These implementations are also very tolerant to system memory, which is important, especially if you have video as well as audio in your system, where we see system latencies that can run as high as 400 to 500 clock cycles. In the case of the ARC processors, you see very little performance degradation. With some of the competitive cores, it can be substantial. This is, again, Synopsys offers a number of analog, or quite a broad range of analog IP for audio input or output. We actually verify up to the interface because we don't know what process you're going to be building your chip in. So this is all digital. This is all process specific. So you can use any of the A to D, D to A's with the audio subsystem. Again, it's fairly verified. You just plug them in. It's very easy. Now, on the software side, we do offer, it's a complete stack, so you don't have to do anything. This is the hardware portion down here with the software on top of it. It completely supports the subsystem, and in fact, we also give you a plug-in for the host environment. So from the programmer's perspective, the guy that's writing the code for the host environment, the subsystem looks like a series of function calls. It is a very clean implementation. You don't need to do anything to implement this. Now, if you want to, we actually deliver the hardware portion as RTL, and we deliver the software portion as source code. So if you want to mess with it, have at it. There's enough rope there to hang yourself if you want to, but you don't need to. You can use it as is right out of the box. By the way, it takes about an hour to configure this system. So within an hour, you can be ready to run, literally, audio with any codecs, because we have the full range. The codecs plug seamlessly into this framework, so you don't spend a lot of time trying to figure out how to interface the codec into it. You just plug them in and go. Within an hour, you can have your whole subsystem ready to go. And if you're doing it in a virtual environment, if you have the virtual environment, your programmer can be programming within an hour, writing code, checking it out. This is a partial list of the codecs that we offer. We have the full range from Dolby, DTS, SRS, Microsoft. and many, many more. The whole list is on our website if you're interested in looking. And these, by the way, are all optimized for the ARC processor in terms of minimizing the bandwidth that's required to run them, as well as minimizing the memory footprint. Also, we have all our codecs certified. So we actually go back to Dolby when we do a codec. We give it back to Dolby, and we have them certify that. We do that with all our codecs, whether it's DTS, SRS, Dolby, or all. And what that means is it's much easier for you when you develop your product, because they're going to require you to certify that their software is running properly on your product. And because we've already pre-certified that, it makes it very easy for our customers. This is just more about the virtual environment. Again, Virtualizer supports quite a broad range. The virtual environment, essentially what it does, it lets you model the hardware and then write software. So it gives you a very sophisticated environment to develop your software code. We just announced yesterday, in fact, a transactor capability that allows you to connect this virtual environment to our FPGA or HAPS environment. So you could run the audio subsystem perhaps on an FPGA board and do the host in a virtual environment. So you get a very clean interface, and you can put both together. This is the HAPS board. I actually brought the demo in here for the audio subsystem for another purpose. That's what it looks like. It's implemented on a HAPS 51 board. That's a Vertex 5. With the host and the subsystem in that Vertex 5, we're using about 20% of the FPGA, so it's a very small implementation. But it runs at good speed, and we can implement a lot of the audio capability in the demo, even in an FPGA. All right, so the Soundwave subsystem, it's available today. It's a complete implementation, hardware and software. You don't have to do anything. You can if you want, but you don't have to. It's fully pre-verified, which, by the way, is a big deal. Verification takes a lot of time, as you know, in an SoC bring-up today. But it's fully verified, and even though it's configurable, we've verified all the various configurations. We have about 200,000 hours of verification time on the subsystem right now, and that's server hours. We spent 10 man-years developing this. There's 500,000 lines of code in it. It's a very sophisticated implementation. You can take advantage of it and implement it literally in about an hour. It's a complete environment, and we support the full range of audio. I think that's the last slide. It is. So let me back up, because I'm not concerned about Sean's catalog.
Well, that was the last slide, obviously, I guess. Questions for Mike? There's a Cadillac Eldorado in it for you.
There you go.
And a set of steak knives. This is my Glengarry.
I just want the steak knives.
I know. Questions right here.
Sure. Thank you very much. I know this is a relatively new product. Probably it's Genesis somewhere overseas or something. But can you talk about some customers that are already using this kind of product?
Yeah, we don't have any customers that we've announced for the subsystem yet. I'm sure we will within the next quarter or so. And you're actually right, it was developed overseas, in Europe.